Welcome to today's lecture on the Internet of Things. In this lecture, we're going to talk about energy again, and after we looked at modeling energy and sources of energy for energy harvesting in the first lecture on energy, we're going to talk about how to optimize the consumption of energy in this lecture. And like the previous lecture, this uses material from Peter Marvidal at TU Dortmund. So we want to optimize the energy consumption. So we want to reduce the amount of energy consumed by an IoT device as much as possible. Of course, we need to do this because in a battery-driven device, we need to run on battery as long as possible. And on an energy harvesting device, we have so little energy that it's actually required to optimize the energy consumption in order to do something useful. So the challenge really for energy optimization is how can we execute the required functionality of an IoT device and still reduce its energy consumption as far as possible? And in this lecture, we are going to discuss three different approaches. The first approach is to use compiler optimizations and to analyze which compiler optimizations, which are usually performed in order to speed up your program, are actually beneficial to reduce the energy consumption of the program. Then also related to compiler technologies, we try to exploit energy properties of the memory hierarchy. So in modern computing systems, you not only have processor register and main memory, but you have several levels of memory in between. So these are usually caches. Caches are not very energy efficient, so an alternative to caches are scratchpad memories, small, fast, but also very energy efficient static RAMs, which are somewhere on a level between the RAM and your processor registers, and these can be used to optimize energy consumption. And finally, something that you probably know from your desktop or laptop PC is dynamic voltage frequency scaling, or short DVFS. So we'll take a look at how this might impact IoT devices. So let's go from energy models to compiler optimization. So we could simply assume that if we optimize for high performance, then, we in the end execute fewer instructions. So this would automatically imply that we would use less energy. Unfortunately, this is not the case because not every instruction uses the same amount of energy. So there are more more energy intensive instructions, which, for example, access the memory more often. And there are less energy intensive instructions, which means that you can use more of them and still save energy. So the architectural difference between high performance optimization and low energy consumption is actually memory access. So for high performance applications, you usually want to ensure that the bandwidth to access your memory is fully used, so that in every cycle your processor does something useful. You can also access, so read or write, a value in memory. Now, memories, as you can imagine, are some of the components of a computer system which contribute significantly to energy consumption. So, if we want to achieve low energy consumption, we would in turn actually try to access memories, energy hungry memories, as little as possible. And if they are not used for quite some time, we can actually put them in sort of a standby mode where they only retain their contents but don't use a lot of energy. So we can deduce, if we keep values in CPU registers, so internal to the CPU, then we would save energy because we wouldn't have to load them from memory or store them into memory. And our bit of C code in the middle is a good example for this. So this is just an example that somehow goes over this array, dereferences the array, adds some of the element, and that's more or less it. This code doesn't really make much sense, but it serves to demonstrate the difference that can actually occur here. So for example, if you go for the fast code, on the left-hand side, this is ARM machine code. You see, this actually has fewer instructions, and to execute this loop, it takes 2096 cycles. Now, on the other hand, the code on the right-hand side is obviously longer because it has more instructions, But you can see it mostly uses add and move instructions, so these are always internal to the CPU. And it only has one single memory access instruction, the LDR, load register instruction. So this means even though it does much more work on the CPU, it uses instructions here which are less energy intensive. So amazingly, the code on the right-hand side is slower. Well, it uses more instructions, so that's not too surprising, I guess. So it takes 2,231 cycles compared to 2,096 cycles. But if we look at the total energy consumption of that piece of code, then the code on the right-hand side is about 15% more energy efficient. So the code on the left-hand side uses 19.92 microjoules, whereas the code on the right-hand side, even though it has more instructions and it still has the same number of loop iterations, we don't reduce the number of loop iterations here, so we're not cheating. Still, it only uses 16.47 microjoules, so around 3.5 microjoules less than our fast solution. So this means that when we want to use compiler optimizations to save energy, we actually have to take care about their energy effect, and we cannot just blindly use every compiler optimization out there and hope that it improves our energy consumption. Right. So, uh, some of the compiler optimizations which are, as we've seen, usually done to improve execution performance, actually also reduce the energy consumption. So we just need to figure out which are those. So one good example is the reduction of operator strength. This means we have an operator which is usually very expensive to execute, for example, a multiplication, and we can replace a multiplication by a shift operation and an add. For example, we can replace a multiplication by 4 of an integer variable by just shifting the value of the integer variable by 2 places to the left. We can also add by something which is not a power of 2. So for example, we can multiply by the number 5 by first multiplying by the number 4 and then just adding one element, and we've seen the multiplication by 4 can be replaced by a left shift by 2 bits. So we no longer have to execute an expensive multiplication where we have to take care of carries and subsequent adds and stuff like that, but we only use a very simple bit shift operator which just moves a bit position and nothing more, and a relatively inexpensive addition. Some other optimizations might also be useful. For example, there are optimizations that try to minimize the bit width of load and store operations. So if the bit width is lower, then of course we load less data from memory or store less data into memory. So the memory can save energy there. And in turn, we can try to devise standard compiler optimizations and use energy as a cost function for their use. So this would result in something like on the right-hand side, where we see that if we just use a loop over an array of 10 elements and just calculate C as 2 times the current element plus the last element, then we can actually use a trick, which a compiler would also do. So you see when we run this loop on the left-hand side, for example, in iteration 2 of the loop, so I equals 2, we would access A of 2 and A of 1. Now in iteration 3, we would access A of 3 and A of 2. Now A of 2 was already loaded into the register before, just because we needed it for the previous iteration as the I operator, and that is the I minus 1 parameter here for the next iteration. So this means if we manage to cache this value, so if we store it in a processor register, then we can actually save energy because we only have to do each load of each array element once instead of doing it twice as on the left-hand side. So this in turn leads us to the code on the right-hand side. So we actually use registers R2 and R1 now, and we cache the value of the current element here in R1, which we use as the ith element, and we always have the previous element stored in R2. So This is initialized in the very first line on the right-hand side as R2 equals A of 0. So this loads us our very first array element, and then we just copy R1 to R2 in every loop iteration. So AI turns into AI minus 1. And this means we don't have to use 2 loads per loop iteration, but only 1 load from memory. So each access to A of I is a load from memory. And this saves quite a lot of energy. Right. So this is pretty useful here. And of course, you can imagine we're not doing a compiler's course here, but there are thousands of different optimizations out there. So you can probably imagine there are other optimizations which might actually be useful for reducing the energy consumption of code. So other optimizations that can be used are, for example, energy-aware scheduling of instructions. So very often a compiler tries to change the order of instructions on machine level, and it can do this as long as the meaning of the program, so the semantics does not change. So if we do an add first and a subtraction after, or the other way around, doesn't really matter as long as no variables are involved in both of these operations. So the goal for energy-aware instruction scheduling here is to try to reduce the number of signal transitions. So we've seen that signal transitions are a major contributor to dynamic power consumption in chips. And this is pretty popular since this is very easy to do. As a post-pass optimization, we don't even have to change the compiler. We could actually use simply the assembler output from a compiler and then run a separate energy optimizer on this output code. We could also do energy-aware selection of instructions. So, for example, if you want to compile a piece of code, as we've seen in the previous slide, with the strength reduction, we could either use a multiplication or we could use a strength reduced version here. And there's quite a number of different optimizations which work with this. So you choose among the set of valid instruction sequences on machine level to implement a certain, for example, piece of C code, and then you select those that you know minimize the energy consumption. And this, of course, requires information about the energy consumption of instructions, so this can make good use of the instruction energy model, which we've described in the previous lecture. And finally, you can already use the compiler to exploit the memory hierarchy, and there are huge differences between the energy consumption of small but fast memories and large and slow memories like DRAM. So when you look at predictions from a couple of years ago, computer architects actually predicted that future memory systems in computers would actually exhibit 3 key problems. First, we have a problem that memory speed is not getting faster as fast as CPU speed. So the faster your CPU becomes, the longer it has to wait for data from memory because, like, imagine CPU speed might, for example, increase by 10% every year, just as an example, but memory speed only increases by 2%. So you have quite a lot of distance between the speed of CPU and memory, even if they started out on the same speed after a couple of years. Energy and power, of course, we're talking about this at the moment, are the other key problem for future memory systems in computers. And finally, memory systems can take variable time to access them. For example, in DRAMs, you can have things like a refresh of memory information. And if this refresh happens while you're trying to access the memory, then your memory access has to wait. So it's very hard to predict how long a memory access, a read or write to, for example, a DRAM memory actually takes in your system. And this is especially critical if you want to build real-time systems, which are relying on a property we call the worst-case execution time in order to keep to all the deadlines that are imposed by the physical environment here. And unfortunately, speed, but also energy consumption, increase superlinear with increasing memory sizes. So we have this diagram on the right-hand side here. We have the memory size in bytes on the x-axis, and the energy consumption and also relative time, access time on the y-axis. And you see that especially the energy, which is the purple line here, this increases exponentially, well, as long as, yeah, your memory sizes go up. But take care when reading such diagrams, because it's always important to look at the scales on the axis. So this is a bit mean because it has a logarithmic scale on the x-axis and a linear scale on the y-axis. So maybe it's not as bad as it looks. Try to figure out with your background in mathematics uh, what actually the relationship of memory size to energy consumption is. So we already looked at compiler optimizations. So compiler optimizations are also closely related to this second technology to reduce the energy consumption. And this is by using the memory hierarchy and especially a special part of the memory hierarchy, which is usually present in microcontrollers. And this technology is called a scratchpad memory. So a scratchpad memory, as the name says, is a memory, but a very special one. It's a very small memory, it's very fast, but it's also, because it's small, it's energy efficient. And it's also closely coupled to the CPU, so very often it's on the same chip as the CPU, which makes it quite a bit faster to access than RAM, which is external to the CPU. If you are using ARM processors, then ARM uses their own term for this. This is called a tightly coupled memory, or TCM, in ARM terminology. There's a typo on that slide, sorry. So essentially, a processor can access scratchpad memory like it accesses normal main memory. So that's major differences to caches. Caches are not visible in the address space. So a cache is what we say transparent to the CPU. So the CPU always loads a value from an address, and if it happens to be in cache, then this value is loaded fast. And if it's not in cache, then you get a cache miss, and then the CPU has to go to main memory and look for the value there. Now, an SPM does not do this transparent overlay over main memory addresses, but it's just an address range of its own. So if the processor wants to access memory in the SPM, then it actually has to use the appropriate address. We see this in the middle diagram here. So we have a big address space here from 0 to the end of memory, FFFF, and somewhere in there, there's actually a memory range where scratchpad memory is located. Whereas other memory ranges here, which we don't show, maybe the ones below scratchpad memory here, going to the top of memory, might be RAM, and the other memory range on top of scratchpad memory, so starting at 0, this might be your internal flash memory for your firmware. So this also means while you don't have to do anything in software to use a cache, you need to change your software in order to access scratchpad memories and make use of them because they have different addresses compared to your normal RAM. And here on the right-hand side, you see ARM7 TDMI cores. So you see the CPU is actually just like less than 1/3 of the whole chip on the lower right-hand side. A lot of this chip, which is an old microcontroller, is actually used up by the implementations for all the peripherals, from UARTs to SPI to Ethernet to whatever is available on that chip. And there's quite a lot of RAM on the top right-hand side here, which is scratchpad RAM. So that's one of the reasons why scratchpad RAMs are relatively small. They are what we call static RAMs. So static RAMs actually don't need refresh because they keep their contents due to the circuit technology used to create them. But unfortunately, this circuit technology is much more space intensive than the one for DRAMs. So a static RAM or SRAM uses usually 6 or 8 transistors to implement a single bit memory cell, whereas in a dynamic RAM you only use one transistor and a small capacitor. So essentially, if you have the same area of chip available, a DRAM would have much higher capacity, but DRAMs have to be refreshed because they store information in capacitor. This capacitor is slowly leaking energy, so we have to refresh that information that's stored, this bit that's stored in each capacitor from time to time, and the SRAM due to their circuits just keep their values until power is lost. So to use SRAMs, we could try to use regular compilers and see which functionality is there. So for some compilers, you can use a so-called pragma. So pragma is just a specific construct which gives instructions to the compiler how to compile something. So you can use special pragmas in the C code to allocate a certain, for example, variable or data structure to a specific section in your file. So for example, here you have a pragma for ARM that says we have our element foo in a section called read-write data and an element called bar in a section called read-only or RO data. So for example, int x2 equals 5. Well, it's a regular int variable, so it's read-write variable. This ends up in a section we call foo, so the data part of that region. Whereas if we have a constant, like the second declaration here, int const z2 of 3 equals 1 to 3, this would end up in a different section called bar. And now we can use something we call a linker script. So a linker script is responsible for telling the, well, compiler, or to be precise, the linker, which produces the final binary. And the linker script actually instructs the linker which sections of the code go into which addresses. And since we know the address of our scratchpad memory, we could, for example, instruct our linker script to put a certain section or segment of our binary executable file directly into scratchpad memory. So every access to these instructions in the scratchpad memory or this code in the scratchpad memory would be much more energy efficient here. So on the bottom, you see a short description of an excerpt for such a linker file. So you see there's a ROM somewhere here, so read-only memory, which contains the read-only data in exec ROM, and it starts at address 0. And we have a DRAM here, a dynamic RAM, which starts at address hexadecimal 18000 and has a size of 8000, so 32 kilobytes. And this would contain the read-write data plus RW and also the ZI data, which stands for all the zero initialized variables here. So all the variables that you just declare but do not initialize directly with the declaration. And of course, you could add a second section for RAM, like an SRAM with our SPM memory, and you could put certain of these sections then into this specific memory. Now the problem is, well, this works already pretty well, but it's static. So if your program behavior changes, might benefit from other variables being in your scratchpad memory. But since the linker script always fixes the addresses of variables in memory, well, you can't change this while your program is running. So you need a different approach to do this. Nevertheless, if you just use a standard compiler and a post-pass optimization for this, you can already save quite a bit of energy in some cases here. So this is just a mix of sort algorithms here, and you see the energy consumption, which is a purple bar, goes down significantly. So if we have a scratchpad size of 0, so no scratchpad at all, we use about 11,000 microjoules for a certain example, and you see that there seems to be a local optimum at a scratchpad size of 1 kilobyte for this example here, because afterwards our energy goes up again because we still have to run and operate this larger memory. So there the benefits we gain from storing in variables are slowly storing variables in scratchpad memory are slowly eaten up. And of course, the instruction cycles, also the red bars here, still go down, but not as significant as the energy consumption. So this uses the measured processor and external memory energy from Steinkes experiments with the ARM17MI, and also uses values from the Cacti memory energy simulator for the scratchpad memory. So here, this approach that's presented here combines these methods. So this is quite an old diagram already, but it neatly shows which benefits you can actually gain from using scratchpad memory. So in the best case, we reduced the energy consumption from 11,000 microjoules down to like around less than 3,500. So that's a factor of more than three. And of course, this means in turn, if this would be would hold for the whole program, then we could run our processor on the same amount of energy in a battery or a capacitor for three times as long. Now, of course, the specific numbers will change with the technologies in use, but the algorithms behind this will remain unchanged and can benefit also from new technologies here. Now, if you are willing to actually move code and data around depending on which part of the program you're currently executing, and you found out for which part of the program which code and data parts in scratchpad memory make the most sense, then you can actually save quite a lot of more energy. So this relies on having what we call an energy-aware compiler. So one of these was developed in the group I was working in 10 years ago at Dortmund University. And so the question is, we have a small scratchpad memory, so we cannot store all instructions and all data of our program in this small scratchpad. So we have to select which parts of the code and which parts of the data are stored in scratchpad memory and which remain in main memory. So we can have something like a non-overlaying or static allocation. And for these, we actually have data objects or code objects K, and we calculate the gain by putting it into scratchpad GK for this object K, and also we try to figure out its size, so the number of instructions or the size of the data. And then what we try is to maximize the overall gain, capital G, and this is the sum of all the gains for all the memory objects. And the condition that we have to respect here in our optimization is that the size of the scratchpad memory, just called it SSP, is sufficient to fit all the different objects K we consider putting into our scratchpad memory. Well, they cannot be larger than our scratchpad memory, obviously. So all of the objects we put into scratchpad memory at the same time must not be larger than the size of our scratchpad memory. And this is a typical optimization algorithm. In this case, we use the knapsack algorithm to solve this in order to pack as many of the objects which are reducing the energy consumption into scratchpad memory. Now, if you can do this statically, but you can also do this with an overlay method. So you do dynamic allocation, which means you move objects back and forth from main memory to scratchpad memory and the other way around. So you can also evict objects from scratchpad memory. But of course, you have to still store them somewhere in DRAM if you need them later. And of course, here the optimization challenge is that the benefit from moving an object into scratchpad memory must be larger than the cost for moving it and moving something else out to make space for this new object. So if you want to migrate code and data, you can use a mathematical approach we call ILP, or integer linear programming, which is essentially a set of inequations we use to optimize a given number. So I'll not go into very many details on these, but it's interesting to see at least what is modeled in such an ILP. So for example, we have certain functions here. So we have a function capital S for each variable k in our program. It just gives me the size of the variable. So a character in C might be 1 byte, an int might be 4 byte, and an array of 100 ints might be 400 bytes in size. Then we need to know how often each variable k is accessed. So this is n of the variable here. So the more often a variable is accessed, obviously, then it makes more sense to put it into scratchpad memory because we save energy with every access. Yeah, this access and the energy we save with it is actually modeled at the next variable, e of var. So we actually need to know about the energy difference. So how much energy can we actually save per access to this variable if this variable is migrated into scratchpad memory. And then, of course, we can calculate the overall energy saved if a variable var k is migrated. So this is just the energy per variable access times the energy times the number of accesses to this variable here. And finally, we have a decision variable x for a variable k, which is just an indicator. If our variable is currently in the SPM, then it's 1, and otherwise it's 0. And k is just our set of variables, which means we look at all the variables in our program. We can do this in a very similar way for functions, which we would call I, then here, and we could copy functions into SPM or leave them into DRAM. And then, of course, it's not an access to a function, it's how often a function is called, which becomes relevant here. And now with integer linear programming, we can actually try to optimize our energy. And we do this by optimizing and maximizing the sum of all of our variables, so k out of the set of all variables here, so that the decision variable, so is it in SPM or not, times the energy of that variable, which is the overall energy considering the amount of accesses, plus the same for instructions here for certain functions is maximized. So E is the energy that's saved. So we're trying to maximize the energy saving for all the variables which have x equal to 1, so which are in scratchpad memory. And this is subject to the constraint, which we already mentioned on the previous slide. This constraint simply says that all variables we want to put into scratchpad memory, plus all the functions we want to put in that scratchpad memory, still are small enough to fit that scratchpad memory when we add off all of their sizes together. So essentially, all of the variables, all of the data we put into scratchpad memory taken together, their size must be less than or equal than the size of our scratchpad memory, because otherwise we'd run out of scratchpad memory, obviously. Yeah, so you can do things like code allocation in scratchpad memories. You can also allocate your runtime stack in scratchpad memory. So runtime stacks are usually very often accessed because they keep local variables and also return addresses. So if you make use of a lot of functions, then actually you also make use of a lot of scratchpad memories. And you can see the curves here are looking quite similar. So depending on the scratchpad size, you can save energy up to a factor of more than 5 with just this 2 kilobyte scratchpad size, considering a mix of different benchmarks. So this was obtained using the energy aware C compiler ENCC, which is available from Dortmund Technical University. We can also look at savings we can achieve for the memory system alone. So on the x-axis of this diagram here, we have the total capacity of our scratchpad in bytes. On the y-axis, we have energy savings now in percent. And we can see, depending on the different benchmarks, so each of these colored lines is a different typical embedded system application, a typical embedded benchmark. So these behave quite differently for different scratchpad sizes. And this is quite interesting to look. So if you are running a mix of applications, then essentially you could also try to figure out which of these applications should make more use of scratchpad memory than another. So the final way to save energy we want to discuss here is dynamic processor power management. So most of the embedded processors available today actually support running in different operation modes. So for example, we see a diagram on the right-hand side here. We have 3 different operation modes. We have a run mode where the CPU is running at full speed and uses a lot of power, like 400 milliwatts in our example here. Then we have another mode called sleep. A sleep mode is a low power mode, but it's just, sleeping as the name says. So this would be a very, very, very power efficient mode. So this only takes 160 microwatts, so less than 1,000th of the run mode. But you can see it takes quite a lot of time to actually get into sleep mode, so 90 microseconds. So you need to have energy for this 90 microseconds, and then it takes even much longer time to wake up. So almost 1/6 of a second, 160 milliseconds, is required to wake this specific processor this data was taken off from sleep mode. So an alternative is something in the middle, which is called the idle mode. This is much less energy efficient than sleep mode, but it only takes 10 microseconds to get from run into idle mode, and also 10 microseconds to switch back to run mode. So if you need to switch back to run mode fast, then maybe it makes more sense to put a processor into idle, which still saves around 90% almost of the energy, and enables a much faster wake up. And the interesting thing is we can also go from idle to sleep mode. So if there's a power fail, we can maybe run on a little backup power we still have available somewhere, and leave the processor in sleep mode, in which it still retains information. So the example here is from an older ARM processor from DEC, the strong ARM SA1100. And yeah, this is still the basis of all the sleep modes you have available today. Of course, processors today got much more complex, so they have additional modes. So that even desktop and laptop PCs have sleep modes nowadays. So different power saving modes, which are also used from, for example, Windows or Linux to conserve energy. So if you want to work with dynamic voltage frequency scaling, then first you need to consider the power consumption of a CMOS circuit. And here we only look at the dynamic CMOS power consumption, so we're ignoring the leakage currents, even though they're quite big. So the power consumed by a CMOS device is, a switching activity multiplication factor alpha, multiplied with the load capacitance of your circuit, multiplied with the square of the supply voltage, and multiplied with the clock frequency. So essentially, the higher your clock frequency, the higher supply voltage you need to supply to your chip, and this means your power rises non-linearly. So essentially, you want to keep the frequency down, which also enables you to reduce your supply voltage in your chip. And the problem with this is that the lower the supply voltage for your chip, actually, the higher the delay for your CMOS circuits is. So you cannot run a circuit at a low voltage with a high frequency, because then this would mean that your signals would never arrive on time, or in some cases not arrive on time. So your computer would actually calculate the wrong results here. So essentially, this depends on the difference between the supply voltage and the threshold voltage, the voltage needed to switch between a 0 and a 1. And you see, this is also dependent on the capacities of a chip, the supply voltage, and the difference between the supply voltage and the threshold voltage squared. So essentially, this gives you a time, and this time is the reciprocal value of the frequency you can run this at. So this time gets longer the lower your supply voltage is. So this means if you can decrease your supply voltage, you can reduce the power consumption quadratically. But the good thing is you reduce the frequency only linearly, so the runtime of algorithms is only linearly increased, whereas the power consumption is reduced quadratically, which is a very nice property to have. And this is an example for the successor of the strong ARM processor we've seen in 2 slides ago. So this is the X-Scale processor, now built by Intel, because Intel took over that division by DEC that produced these strong ARM processors here. And we see that we have very different frequency essentially bins here. So on the left-hand side, we have the Intel strong arm we've seen before, and on the right-hand side, we have the newer Intel X scale here, which scales to much higher frequencies. But we can also see that, so the green bars are the computational power, so the number of millions of instructions per second that can be executed, whereas this purple bar are the related energy consumption. And you see that, for example, for 600 megahertz, you have half of the computing power of around of this 1 gigahertz frequency for the X scale, but only a quarter of the energy consumption. So that's where your quadratic factor actually comes in very nicely. Right. So Uh, what else can you do to save energy? Well, you can have more processing units on a chip if you want, or more processing units in a single processor that, for example, can do additions in parallel. So we see that a low voltage parallel execution is more efficient, energy efficient, than a high voltage sequential execution. So for this, we can look at basic equations. We know that the power is proportional to the square of the supply voltage. The frequency in turn is proportional to the supply voltage itself. And the energy to run a program is the integral over the power, or we just simplify it here. The energy is just the power times the runtime of a program. And the runtime of a program, of course, is proportional to the inverse of the frequency. So the higher the frequency, the lower the runtime of your program is. And if you do parallel processing, which enables you to do a number of operations in parallel per clock cycle, let's call it alpha operations, then, well, to do the same amount, to execute the same amount of code, you can reduce the frequency by this factor alpha. So if you can do 4 instructions in parallel, and you want to finish at the same time, you still can reduce the operation frequency to 25% of its original value, because now you do 4 things in parallel in the optimal case. The supply voltage can also be reduced linearly here by the number of operations per clock cycle. The power for parallel processing is divided by the square of the operations per clock, and the power for alpha operations per clock. We need to consider that we're now doing more in parallel here. It's just P divided by alpha. The time, that is our assumption, should stay the same. So we just want to use more operations to reduce the frequency in order to enable a program to finish at the same time as before on a single processor. But the energy to run a program now in turn is just the new power multiplied by the same time as before. So this is the original energy of our original single sequential execution divided by our parallel operations numbers per clock. Of course, real life is much more complicated, so these are very rough approximations, so just rules of thumb. But this in turn indicates that scaling the supply voltage makes sense, especially if you can use parallelism in your processors like VLIW processors, which are relatively common in DSPs, vector operations, which are more and more common also in smaller embedded cores, and even multi-core processors, as long as you have enough independent tasks to do. So here we have an example for dynamic voltage frequency scaling for a processor with 3 different voltages, and we have 3 different use cases. So case A here is we want to execute the complete task as soon as possible, and we have a task that needs to execute a billion cycles, so 10 to the power of 9 processor cycles within 25 seconds. And we see that if we reduce the supply voltage VDD, then the energy per cycle is also reduced. The maximum frequency obviously needs to be reduced linearly, and the cycle time also goes up linearly. But the energy, that's the important thing. If we reduce the supply voltage by half, is actually just 25% of the original energy per processor cycle here. And so we have this diagram here showing the time on the x-axis and the supply voltage squared on the y-axis, which gives us an indication of power and time. So the area of the rectangle here would indicate the complete overall energy consumption. So we would execute 10 to the 9 cycles at 50 megahertz. So we want to execute the complete task as soon as possible. And this, in our example, would, for example, take 40 joules of energy. And the calculation for this is shown on the right-hand side in red. So this would mean in a real-time system, for example, if we had a deadline at 25 seconds, we only need 20 seconds for the whole calculation. So, well, then we have 5 seconds left over, which could be used to save energy by turning the processor off. But the question is, does this make sense? So another example would use two different voltages of our 3 voltage processor here. So we have the same table as before. And then we could actually make use of the fact that we had 5 seconds left over because we were just finishing 5 seconds before the deadline. And so this could use 750 million cycles executed at full speed at 50 megahertz. And then we could actually slow down the processor so much that we could actually fill the remaining 10 seconds from 15 to 25 by just running at 25 megahertz. So this would reduce the related power consumption quite significantly. And as you've seen, we always take the area under of the rectangles here, taken together here. So this reduces the energy already. So we end up using 32.5 joule only compared to 40 joules on the previous slide. And finally, if we have 3 voltages, we can actually try to choose the optimal voltage among the three to execute the code. So the optimal voltage is the voltage that exactly meets, or as good as possible meets, our real-time requirement. So we're exactly finished at 25 seconds, or maybe at the closest to 25 seconds. That's less than 25 seconds. We still have a billion cycles to execute, and if we can execute these at 40 megahertz, then we only use 25 joules of energy, and this is compared to 32.5 or 40 joules which we've seen in the previous slides. So if we can switch voltages dynamically at runtime, and we have different voltages to choose from, and we know these relations between energy consumption, speed, and essentially the frequency, then we can use an optimal, well, we can say working point for the processor to execute code exactly as fast as required, and then save as much energy as possible. So we've seen 3 different approaches to save energy in computing systems. Of course, there's many more approaches out in the wild and used in industry. We cannot discuss all of them here, but I think the 3 we've discussed are pretty prominent approaches. And these are obviously relevant in embedded systems and in turn in all IoT applications, all IoT nodes, which are energy sensitive. And we showed 2 examples here, assignment of code sections to scratchpad memory, and also dynamic voltage frequency scaling, which are both useful and can also be combined to save even more energy. We've seen SPMs as a component of the memory hierarchy that can often be used to assign code and data to it to save energy. And this could actually be understood as a cache management, which is not happening automatically, but it's happening manually. So your software decides either at compile time or in a more sophisticated way at runtime which parts of your program and so code and data to put in scratchpad memory, and for dynamic approach also which parts to evict at runtime in certain points and which to load from DRAM again into scratchpad memory. And we've seen that scratchpad memories are more energy efficient than caches. Well, they both use SRAM usually, but caches always need to figure out if you have a cache hit. So a cache always needs a very large amount of comparators, which have to run for every cache access. So this is what makes caches relatively energy inefficient, and SPMs don't need that comparator because they're accessed by an address. So you always know that there is an SPM data value at a certain address. So this makes it more energy efficient. Now, there are also more modern approaches combining caching and scratchpad memories for even more optimized ways to do this. And then we've seen dynamic voltage frequency scaling. So we've seen that we can adapt the voltage and the frequency which go together of a CPU, so we can clock the processor as fast as required for a given task, but not any faster. And if we don't need the processor, we can also use idle or sleep modes to reduce the power consumption even further, but we have to consider the time it takes to transition into and out of these special power saving modes. And most approaches actually have quite a number of parameters, so they very often involve complex optimizations. So we've seen the knapsack problem in one slide, and for more complex parameters within equations, we can use this integer linear programming approach. And finally, you can do things like combining real-time optimization and energy consumption optimization. For stuff like this, you have such a large search space that you can actually not consider all the solutions separately, but you have to be very selective using a dynamic programming approach. For this, you could, for example, use genetic algorithms to analyze the search space and then to find what we call a Pareto front of different solutions, which are optimal in one or the other way. Right? So this was our second lecture on energy. We talked about energy optimization in the memory hierarchy, in the compiler, and using dynamic watch frequency scaling. And as always, here's a set of references for you to enable you to dig a bit deeper. Now, in the final lecture, in the next lecture on energy and IoT systems, we'll talk about a very special mode, which is very special to IoT, which is intermittent computing. So this revolves around energy harvesting. So the idea of collecting energy from the environment. So you get very little energy. This energy is not always available and it can fail relatively fast. So the question of our next lecture is how your software is able to handle this. That's all for today. Thanks for listening. Bye.